This is Doug Sparks from M2M Technologies, and I'm going to be talking about helium and the issues that we've seen with helium with regard to micromachined or MEMS vacuum packaging of sensors and actuators. A few years ago, people noticed that their Samsung and iPhones were failing when they worked around MRI machines, which bleed out a lot of helium. And there were a number of videos where people would put their phones in a plastic bag, put a little helium in there, and just watch them shut down. Helium has been used for decades, since the 70s, to look for leaks in packages, electronic packages, ICs, and even sensors and MEMS devices. However, as I mentioned, we've seen some issues. Now, a lot of MEMS resonators like gyros or timing oscillators, maybe F-bars, will have what's called a Q of the resonator, and that's a signal sharpness, a peak sharpness. The higher the Q, the more sharp the resonator signal peak is with respect to its frequency, and that's shown here in the top left. If you take these resonators, put them in like a bell jar, and gradually pump down the chamber, lowering the pressure, you'll see the Q gradually increase. And that's shown on the bottom left. Just an example of a laboratory vacuum chamber with some electrical feed-throughs. Now, what we've seen when we do what's called the helium bomb test, and that just refers to putting parts in a pressure chamber and then pressurizing it with helium, usually using a gas cylinder. That's kind of the picture in the bottom right. As you let that part soak in helium, in some cases, the Q will gradually decrease over time. The frequency may increase over time, and that's due to gas damping. The gas dampens the resonator, reducing the Q or shifting the frequency. It's really been interesting. You can just have a short amount of helium pressure exposure, say a very short helium bomb test. You can measure the Q, it looks pretty good, but then over time the helium will seep in through different seals or crevices and gradually decrease the Q after just a short helium exposure. So you might think initially, hey, the part looks good in helium, but then over time your Q value will decrease. What I decided to do, because I'd seen this many years in the industry with wafer-to-wafer bonded parts especially, is I took a bunch of different parts. A lot of them were commercially available parts, absolute pressure sensors, vacuum sealed resonators, Pirani gauges. I took them, some were packaged in welded TO cans or gold tin soldered ceramic packages, which is the industry military standard for hermetic parts. And then a lot of them were just wafer-to-wafer bond seals. I looked at those things, did the same exact helium pressure in the same, you call it the same bomb or pressure chamber, and then looked at results. For an absolute pressure sensor, which has a reference vacuum, when you start getting leakage into that vacuum cavity, you start seeing the offset voltage increase. And this shows some examples of some automotive pressure sensors. We call them MAP for manifold absolute pressure sensors. Both glass reflowed frit bonding, which was the Freescale part, NXP. Anodic bonding, which was made at Delphi or Merit. And we saw this offset voltage gradually increase over time with helium exposure. So how many days did you sit it in? How many days was it pressurized? And then a subsequent increase in the offset voltage. It was also interesting. We took resonators and pressure sensors and put them in other gases: nitrogen, air, argon, methane, hydrogen. We didn't see any change in Q with those gases. So kind of interesting, we were seeing the big Qs, we were seeing big Q drops in a short period of time with helium, but with hydrogen, for example, we didn't see that. And that begs the question, because if you look at helium and hydrogen, a van der Waals radius, hydrogen is actually smaller than helium. One of the theories I thought was it was an infusion effect. So there was a tiny gap in the wafer-to-wafer bonding seal, and it just took time for that small helium atom to go through there. However, hydrogen's not is actually smaller than helium, and I wasn't seeing the effect. So perhaps hydrogen is reacting with the hydroxyl atoms at that interface. Maybe the silicon's gathering it, whatever. I didn't see the problem. I didn't see the issue with hydrogen. We've also seen helium. Others have reported that helium can diffuse through glasses relatively easily, and of course that would be a factor with anotically bonded silicon to glass wafers or glass reflow chips, maybe even silicon direct bonding, because really the seal is a native oxide or maybe a thermal oxide interface bond. One thing to note when you're thinking about helium and this problem of Q decreases, noble gases can't be gettered. So if you're using thin film getters to lower the pressure of your cavity, it's not going to be impacted by helium. Okay, so I did a number of different direct experiments. I ended up using absolute pressure sensors, coating the backsides of the wafers with different materials, several solders, low melting point solders. And the reason I did that was because, as I mentioned, gold tin reflowed Kovar lids on ceramics showed great resistance to helium, totally hermetic, as did the welded Kovar metal cans. And I did find at least one solder combination. I didn't see this offset pressure change over time when pressurized in helium. So there is a possible solution with silicon to silicon bonding. Again, these were silicon to silicon bonded parts with reflowed soldered seals. So there is a possible solution for wafer level packaging. You just got to change your materials. Now, just to wrap up, what are the implications of this? MEMS devices, whether they're pressure sensors, flow sensors, resonators, they're often used in gas sensors. Welding cover gases often use helium. Scuba diving, MRI machines, semiconductor processing. Helium is a really popular backside wafer coolant glass, and sometimes it's used in plasma deposition and plasma etch processes as a mix gas. Of course, if you're doing the mill standard helium bomb pressure testing, your devices are going to be immersed in pressurized helium. So you've got to think that what's the application, what's the device, what are the materials being used, are they resistant to helium diffusion, is the sealing method hermetic, truly hermetic in high pressure helium, maybe it's not. And then again, rethink your reliability testing. You may want to move away from a helium pressure test and do something like krypton or neon, for example, as your pressure gas to look for leakage paths. Feel free to contact me. Here's my contact information below if you want more information and you're thinking about using helium, using MEMS devices in a helium application, or just hermeticity in general. And of course, again, like and subscribe my channel. Thank you.